Well, thank you very much. It's good to be back again. And as Paul said, I'm going to be talking about something completely different. So as you probably recall, I was here talking to you twice about various aspects of hack. And this is in a different vein because we are now talking about software development practices, community software, and other things. And I think Andrew did a great job this morning about talking about Flash and how that community is built and developed, maintained, and how that affects the code and how that affects the users and what it can be used for and all those kinds of things. And I'm going to use LLVM as another case study, as it were. It is a larger project, as it turns out, and one with which I'm quite intimately involved. So I'm going to explain first what it is, those of you who don't know, and then how the community is structured and organized, what kinds of rules and practices are involved in that, and how to make a community that is welcoming to newcomers and also useful to established contributors. So hopefully all of that gets put together in some package that explains how this works in practice. I'd also like to convey the message. I'm going to say this up front because I'm not otherwise sure I will implicitly make the point that contributing to large community projects is not scary. And it shouldn't be scary. If it is scary, there's a problem. And I know at least with LLVM, I think there really isn't that kind of problem. Most projects don't have that problem. But nevertheless, it can be quite intimidating if you haven't done it before. So that having been said, let me get started. At the end, I will also talk a little bit about why I am specifically interested in LLVM and the kinds of things that I'm using it for. But I'll get to that later. So first, so what is LLVM? I believe the official project website now says that LLVM stands for nothing. It did originally stand for the low-level virtual machine, but it's not a virtual machine, so sort of a bad name. And at this point, they decided, well, we're not going to change the name, but we'll just say it doesn't stand for anything. I'm not sure how well that works in practice, but there you go. What it is, in practice, is an open source infrastructure for developing compilers and other kinds of software development tools. And the next question is, well, who develops it? And one of the very interesting things about LLVM is that it's developed by a lot of different people. And in fact, it's developed by a huge consortium of companies, many of which you've heard of, primarily Apple, then Google, I would say Intel, AMD, NVIDIA, ARM, IBM, and a lot of other companies as well. In addition to that, there are a fairly large number of academic contributors. And then there are individuals and people who just think it's cool or fun or whatever they want to, however they motivate themselves. And all of these people come together to develop a product which is of quite high quality and quite useful. The key thing about this that I would like to point out is, especially among the companies, but also true of the academics, is that a lot of these companies are competitors of each other. And it's not the kind of thing where you normally think, well, all these people are going to come together and put their differences aside and do something for the common good. And in some sense, that's true. I mean, they're not doing it for the common good. They're doing it to help themselves. But nevertheless, that's why most people contribute to these kinds of projects, is because they get more out than they put in. And nevertheless, there are other kinds of relationships here as well. In addition to these companies being competitors of each other, many of them are also customers of each other. And so there are other kinds of relationships there in the sense that, for instance, completely from public knowledge, right? I mean, ARM would like Apple to buy things from them. And Apple is invested in LLVM. So ARM is invested in LLVM. And Intel is invested in LLVM, et cetera, et cetera. And it goes on like this. And although you might say, well, this doesn't necessarily have a lot to do with academic projects, with science projects, I actually see a lot of the same dynamics with science teams as well. Of course, LLVM also has a number of academics who use this for computer science research. And you can draw a direct parallel, but I think even more than that, in my experience, successful community science projects, just like any other kind of open project, really flourish when they're used not only by people who you would traditionally think of as collaborators coming together to build some piece of software, but also are those projects that are developed by competitors, where different groups come together and work on areas of common, perhaps you would call it infrastructure, and they all actively contribute to this core base code. And yes, they all also have their own proprietary pieces that they keep to themselves and use. But nevertheless, it's the fact that you have such a diversity of contributors. And I think to have such a diversity, you almost by definition have to have competitors that make the whole process work, that give you the economies of scale, the raw number of eyes on the code to really make such a large endeavor successful. So that having been said, I could say, well, how did LLVM begin? And I should point out, I suppose, that LLVM did begin as an academic research project at UIUC. In fact, it was one guy's thesis project, essentially. And it has grown from there, and the development is now certainly primarily driven by the commercial interests. They put in most of the money, which I believe I did a back of the envelope calculation at some point and decided that it was probably at least $10 to $20 million a year if you add in everything, just from the major commercial contributors, not counting any of the academic investment, grad students, and everything else. But I'd like to point this out also because I think it's a really nice example of a project that has transitioned from being purely an academic concern to something that is shared between academia and industry. So, I mean, as a physicist, I work on what you would call astrophysics or cosmology, and there really aren't very many commercial interests in, in astrophysics or cosmology. But I know that a number of you work on areas, or at least I suppose a number of you work on areas because I know represented in HPC there are a number of areas, especially those, where you might say, engineering, chemistry, biology, all these kinds of areas where there is a significant overlap, or at least potentially there is a significant overlap between academia and industry. And I think it's important to keep in mind that software projects, large-scale software projects, can have a lot to benefit from industry participation. And encouraging that is not necessarily a bad thing, although it can come with baggage, granted. Okay. So this is just to point out quickly that the LLVM is also still widely used in the research community. I also like, in some sense, this graph, which is from LLVM's webpage. And in some sense, it doesn't seem like a very, well, it almost doesn't seem good in some sense, because maybe you can't read this, but this is a graph of number of papers per year as a function of year. And there was this huge spike in the sort of 2009, 2010 year. And then it's actually decreased a little bit since then, although I think the 2013 papers aren't on this list. But the reason I specifically want to point this out is because these years were really just about the time when the Clang, the C++ front end of the project, was powerful enough to compile and analyze almost all available codes. And so from a research standpoint, there's a lot that you can do when you have a tool that can be applied to real code bases. And so as soon as that happened, you got this big spike of papers of all of a sudden you had this new capability and people could apply it. So it was a very natural result. And again, I want to point out that that would not have been possible just from the academic contributors alone. There just wasn't enough manpower, there weren't enough people. It was because of the investment from the commercial industrial side of things that that was possible. And a lot of the subsequent papers and research that have been enabled by that have really been quite important in the compiler research community. In fact, I think last year, LLVM won the ACM software prize for, well, I don't remember what it's called exactly, but they give it every year to some extremely useful and influential software project, and this was the winner last year. Okay. So onward with the graphs, I suppose. So next I wanted to say, well, how large is LLVM? Because I said this was an example of a large software project. So what does that mean? So on this graph, you can see that LLVM consists of approximately 1.1 or 1.2 million lines of source code, plus several 100,000 lines of comments, and a lot of blank lines. But that's okay. And it is written mostly in C++, although there is some C and some assembly and some other. I assume other is actually mostly the regression tests, but there's also some Python scripts in the build system and other things. Oh, and I should point out before I go on that this is just for the back end. So Clang, which is the C and C++ front end, for instance, is almost about as large as LLVM itself. So that's another million or so lines of code, plus comments, documentation, and all the other nice things that go along with it. So it's a large project. I would say all told, putting together the entire package, you're probably talking about 2.5 million lines of code. And so you say, well, okay, the next question is how many people, or how active is the project? And so you can see here that you get about 1,000 commits a month is how this project is maintained. And that number has stayed roughly the same over the last several years. But the nice thing about it, in some sense, is that even though the number of commits has stayed roughly the same, the number of people committing has significantly increased. So we're getting more active participants in the project. And so at this point, the number is somewhere around 100. And there are about another 100 or so who contribute to Clang. And there is some overlap, although not as much as you might think. And so, as I said before, the reason why all these people contribute, well, I mean, there are some hackers who just think it's cool. But the reason why companies invest and why academics invest in this project is because they all know that they get out more than they put in. And there are two parts to this. And I think that this is important to mention. So one is that they get a good return on their investment in the short term. Obviously, there's a lot of development going on from a lot of different areas. And all these things add new features. You get to take advantage of new features that are being developed by other people and use them to facilitate your own work. So that's the sort of obvious benefit in some sense. And it tends to be fairly short-term. The long-term benefit, which is equally important but perhaps under-recognized, is the maintenance benefit. So when you have code that you have contributed to this large code base, and you have contributed this code, and it has some unit tests or what have you, and you now get to rely on this large community of people to maintain that code for you. You don't have to worry about updating it when interfaces change or APIs change. You don't have to worry about retesting it every week to make sure that no one broke it. The community does that for you. And that's actually a large investment on the part of the community, but it is an extremely important benefit to the contributor. And I think that the point to make for any kind of community project is that you get both of these benefits, and that's really what makes it worthwhile. Because not only do you get the obvious benefit of taking advantage of other people's features. But you also have a much less onerous maintenance burden on your own code going forward. And if you integrate that out over many years, then it really can be a significant savings. So the next thing I wanted to say was, at least my personal opinion, what is it that makes the project work? Why is it that people invest in this? I broke it down into 3 keywords. Right? So one is quality, then dependability, modularity, and the community. And I'd like to go through them in reverse order. So I'll say more about this later to some extent. But first, no project succeeds without an active community. So the active community is a combination of community infrastructure, which are mailing lists, IRC chat rooms, meetings, social events, all that kind of stuff. And also the culture of the community. And I think that Andrew did a very good job this morning talking about how different varieties of culture can make a big difference to how a software project and a community function. And I'd like to point out just a few key points of what I think makes the LLVM culture work. So first is maintenance sharing. So there's a common understanding that it is everyone's job to contribute to the maintenance of the project. There is no core group of people who are paid solely to do maintenance tasks. It is no one's job to clean up your comments. It is no one's job to fix the fact that you broke the build. It's no one's job to fix the fact that your commit broke someone else's feature. And when you are updating common code, it is your job to make sure that that works for everybody. And the thing that makes this work is that everybody understands this, and everybody contributes. And it is a small but manageable overhead on the amount of time that you put into developing with the project. The second thing is being helpful to newcomers. So it is unfortunately true that in a lot of projects, there is a very condescending attitude that established contributors take towards new people. And while this is unfortunate, one of the things I like about LLVM is that there is a real effort not to have it happen there. So we all recognize that the project will die without fresh blood and fresh ideas and people with different kinds of expertise. And you'll never attract those people if you are not welcoming. Part of that, although not degenerate with it, is respecting all opinions. And I put on the slide with no foul language. So I'll share a quick story, which I think highlights this to some extent. A couple of weeks ago, for the first time that I'd seen, we had people from the Linux kernel mailing list who were upset about some feature in LLVM, the way that it had been implemented. And so they decided that they would cross-post a thread between the Linux kernel mailing list and the LLVM developers list. So this ended up being amusing in several respects. But the thing that I thought was really shocking to me, and to some extent, being that I don't really follow the kernel mailing list closely, was the amount that these people would swear at each other and call each other names, the kind of things that you tell people not to do when they're little. Yeah. Right, and then they grow up and they're like, I can do it now. And within an hour or so, we had people writing back to these people from the Linux kernel mailing list, one of which was Linus, by the way, saying, "We don't talk like that here. Please tone it down." And I think it sort of goes to this issue of being welcoming and being respectful, which is extremely important. The reason why people feel comfortable coming to this community and contributing is because they know that they will be treated like an intelligent human being, even if they are not an expert. Even the experts know that on these mailing lists, there are lots of other experts. So, even sort of among experts, there has to be some certain degree of decorum, and it really ends up being quite important. That having been said, there are also rules, like no foul language, but there are rules regarding code development and other things, and you still do need to be firm about the rules, like rules regarding testing and rules regarding other things, which I'll talk about in a minute. But that all has to be done in a respectful way. So the second thing I want to talk about is modularity. When you have a very large project, obviously not everyone is using it for the same thing. In fact, people normally only use some relatively small piece of the overall project for whatever they're doing. And so maintaining modularity is extremely important. It means that you need to have certain reusable pieces. And in fact, every piece of the project, to the extent possible, should be reusable. One of the primary drivers for many of these people using LLVM over, say, using a more established open source compiler, GCC, for example, is exactly this issue. It's very difficult to turn GCC into a library and embed it in your program. And a lot of the problems people had with trying to do that motivated the design of LLVM. And I just wanted to sort of make the general point that whatever you view as your final product, the thing that you will run as the executable, thing you qsub, it is quite possible that someone else will really want that component to be a library, something that they can plug into their application. As a quick science example, you have a simulation code. You view this executable as your simulation. You run it, it produces an answer, and you design an interface, command line options, and all that other stuff that let you do that in some sort of reasonably efficient manner. Tomorrow, someone is going to come and say, actually, I want to put that thing into a Monte Carlo chain, and I want to run 1,000 of these things of low resolution and do a parameter sweep survey. And now, all of a sudden, you need to have that thing as a library that they can plug into their application, not a standalone executable. So not a priori cutting out potential uses of the code that you've written is an important part of building a large community, because people use these things for different purposes, and maintaining this modularity is important. One of the requirements that we have in LLVM to facilitate this, which I think I also mentioned when I was talking about Hack, was this strict layering requirement. In other words, no cyclic dependencies. This, again, is one of these things that is really helpful when you have people who are using different components for different purposes and need to be able to separate out just the pieces they need. The third thing, of course, is documentation. You need to have documentation on the interfaces, including the internal interfaces between components. These things need to have well-defined contracts. And, importantly, the file formats that you're using also need to be well documented. One of the things that people really like about LLVM is that it has a very well documented, well defined internal representation that, or more than one of them, which can be interfaced with at various levels. And this allows LLVM to be used for a variety of different purposes. So going back to somewhat of the community aspect of this, next key point is dependability. So dependability means different things to different people. On one level, dependability means that the software works and continues to work. That's one way of it being dependable. And so there are various things that we do in order to ensure that that stays the case. First, there are strict rules about regression tests. Regression tests are small tests that are associated with individual changes. If you're fixing a bug, for example, you want to try, whenever practical, to have a small test that exhibits that bug, and that way you add that test when you fix the bug, and that's how we make sure there are no regressions. That's what we call a regression test. In addition, there's a large functional correctness suite. These are whole applications, whole environments that are run through the compiler to make sure that these things that the output is still functionally correct. This is in addition to regression tests. They are not substitutes for each other, and they serve different purposes. For one thing, we can generally run through all the regression tests on a reasonable machine in about a minute, maybe 5 minutes, depending on how fast your laptop is. Running through the whole application test suite, all of the functional tests, that could take several hours. So there is this breakup between tests that are small and fast and are meant to be used for iterative development to catch errors, and then the functional tests, which are run only every several hours, because generally they take several hours to run, and give you more delayed feedback. A part of this also is that we have continuous build and test servers set up. Now, for smaller projects, it's not necessarily important that these things really be continuous, but when you're having upwards of 100 commits in a day, it really does become important that you have an infrastructure set up to do as close to real-time testing as possible. There are all sorts of build servers set up. They build and run tests on all sorts of different architectures and platforms that are supported. Some of these servers run tests under the address sanitizer or under Valgrind to check for memory errors. Is also another extremely important and useful thing. And the rule is that the supported platforms need to be green all the time. Now, in some sense, that seems onerous. You figure we only really need to make sure everything works, when we're going to do a release or when we're doing some important testing. But the problem is that with such a large community, that's essentially true for somebody all the time. Most of those companies that use LLVM in their own products, they take their releases based on some internal schedule that they have. They're often not based on the, what we as the community call a release of the software. They're just taken at some point in time, and each company has its own QA suites and other things that they run, and they have their own procedures for deciding when they're going to integrate this code base into their own products. So it really wouldn't work for a large number of the contributors if we only had a stable software product once every 6 months, which is normally when the releases are done. And so the rule is that for supported platforms, the functional tests and, of course, the regression tests, they have to be green. There should be no failures, essentially, ever. So what happens in practice is that if someone commits a change which breaks some supported platform, then either they have to fix it or it's going to be reverted probably within about 3 or 4 hours. One of the nice things about this is that of all of the projects that I've ever worked on, LLVM has the most stable trunk of any project that I've seen. And for development, this actually is really convenient, because when you're developing your own code, it means that you can almost always pull in upstream bug fixes and feature improvements that you think would be helpful without particularly worrying about the fact that you've now pulled in something that's completely broken and you can't work with. And if you have, you know it's going to be fixed in a few hours. So the last thing is quality. All of these companies and all of these academic contributors would not be using this if it were not of sufficiently high quality to make it worthwhile. There are a couple of things that we need to do in order to maintain quality. But almost all of them come down to one thing. And that is, you have multiple people look at the code and review it before it's committed. This, in some sense, seems onerous, and perhaps, in some sense, explains why the number of commits per month has stayed relatively constant, even though the number of contributors has increased. That is because there's a finite bandwidth for code review. Nevertheless, when you are committing code into this project, you are essentially asking a group of people to spend their time maintaining it, fixing bugs in it, and making sure that it continues to work. So it is only polite to make sure that they agree to do this. The way this works is that patches are proposed to the commits mailing list, and some established contributor, or for major changes, the code owner, has to sign off on these changes before the change is committed. So is it true that every single commit to the repository has been pre-reviewed? No. Obviously, there are a lot of commits from code owners themselves, for instance, who just make at least small or medium-scale changes, and they have what we call a post-commit review. But the thing is that as a practical matter, most of these things are looked at, and that's important. Code review is for not only, it's for design, it's for implementation, it is for stylistic considerations. You're missing a space here, or that comment is not aligned with the other comments. It's both for important things and for silly things. But realistically speaking, if you have 2 million lines of code and you need to keep it readable, well, the only way you really know if code is readable is if someone else besides the author reads it. There really is no other way. There's no magic bullet. There's no rule that you can set about number of lines of comments per line of code. All of that stuff can help. But the only way to make sure your code is actually readable and makes sense is to have another human being actually look at it. And this is really the philosophy that we follow in LLVM, and at least so far, to quite good effect. The other thing, which also goes back to a community ethos in some sense, is that unless completely impractical for some reason or another, changes have to be done, what I'll say, in the right way. In other words, we don't commit quick hacks to fix things or workarounds that aren't really the right way of doing things. Now, of course, you say that and you say, really? All those people agree on what's the right way all the time? Well, no, they don't. Controversial changes certainly get robust discussion before some consensus, or at least some majority opinion is reached on what to do. For small fixes or changes or small improvements, you really can have some idea of what's the maintainable, thoughtful way of making a change or fixing something, and what's the workaround way. If there's some feature that is some optimization that's buggy and causing problems, then the right way of fixing it is not just to turn the whole thing off. That kind of thing really isn't done. And I that is really a community culture thing. It's not true everywhere. It's not a function of size or scope or anything like that. There really has to be a culture of saying, no, everyone really needs to put in the time to do things the right way. And that, I think, ends up being incredibly important to making the project successful. LLVM, I said, is a compiler infrastructure. There are lots of other pieces that go along with it. There are sub-projects. The largest is Clang, which is a C and C++ front end. So you put Clang with LLVM, and you get a C, C++ compiler. GCC is improving, but I think Clang is certainly well known, if for nothing else, for having the most understandable error messages of any C++ compiler. So the people who work on the front end take the front end piece of that very seriously. There are also other projects. So one I'll mention is there's Dragon Egg, which is a GCC plugin. So you can actually use LLVM as the back end and GCC as the front end, if you're so inclined. Another important project, which is part of Clang in some sense, but has its own sort of set of developers, is the Clang static analyzer. This is something that will go through your source code and do a symbolic execution of various functions and try and pick out things that you would sort of like your compiler to warn about, but actually require a bit too much thinking to have it warn about them when you're just compiling. The static analyzer is much slower than, say, just compiling your code, but it produces very interesting warnings. As a side note, it also produces very nice syntax-highlighted HTML files for you to browse your code, which, if nothing else, is also quite convenient. Another project are the sanitizers. So there's, and this is somewhat confusing, but there's an address sanitizer and a memory sanitizer, which do slightly different things. One is for detecting out-of-bounds memory accesses. The other one is for detecting uses of uninitialized memory. There's a thread sanitizer for detecting race conditions. There's an undefined behavior sanitizer for detecting when you've done something in your code that the standard doesn't actually define what the answer should be. This is a major piece of code which has primarily been contributed by Google. Google uses that internally to test and check their own code, and obviously Google has a lot of code to check. And there's libc++, which is a C++11 compliant standard template library implementation. C++11 is almost old at this point, right? So we're going to have C++ 2014 soon. And in fact, since most of what's going to be in that standard has already been decided on, Clang and libc++ already implement large pieces of it. So useful for scientific codes, there's a plugin called Poly, which does polyhedral loop optimizations, which are useful for mostly scientific kinds of programs. And there are lots of other, there are other projects. There are more like computer science-y projects for doing static analysis and other things. And there are lots of independent projects that use LLVM that are not part of the LLVM project, but really go to make this part of the core of a very useful software ecosystem, to use some buzzword. And I've listed a couple of things here, a couple of projects here which I think are useful for HPC. And I'll just go over them quickly. So first is ISPC, which is a compiler for SIMD vector kernels that Intel makes. There's POCL, which allows you to run OpenCL codes on a CPU. There's the GPU Ocelot project, which allows you to run PTX code on your CPU and other things. And for those of you who don't know this, if you have CUDA and you compile it, you get PTX in the kernel. So you can use this GPU Ocelot project to run your CUDA codes without an actual NVIDIA chip, which obviously doesn't necessarily give you very good performance, but can be quite handy for debugging and other things. There's Halide, which was actually mostly an academic project from MIT, I think, but is also now widely used by Google, and it's a special compiler for doing certain kinds of transformations, mostly used for image processing, but I think it could have scientific applications as well. Julia is supposed to be some kind of language that's designed for doing matrix computations and sort of like a MATLAB Lite that's a scripting language, something like this, which was designed by scientists and is supposed to be useful for scientific computing, although I've never tried it. And also, LLVM is used as the sort of just-in-time compiler backend for lots of different scripting language implementations for everything from Python to Lua to, well, there are lots of these things. at this point. And so there are lots of different people who are using this as the backend for tools that are useful to us. So I did want to mention what I'm doing with it and why I care. So primarily, I've been working with LLVM for the last 2 years or so. And I have been making a port of LLVM to the BlueGene queue at Argonne and other places now as well. It's nice because it provides a modern C++ programming environment. I've added support for the QPX vector instructions, which are found on the BlueGenes, and also intrinsics for the vector instructions that are compatible with IBM's compiler. It's been useful because it's really allowed us to experiment with different kinds of optimizations, which you can really only experiment with when you have control over the compiler. For example, on the BlueGene is very sensitive to software prefetching because of the details of how you need to prefetch data into the L1 cache to get good performance. And so I've been able to experiment with how best to do software prefetching in different kinds of loops and have that transformation be done automatically in a way which makes sense on the BlueGene. And that's actually been really key in getting good performance speedups on a number of C++ applications and other things. But it's really something that you can only do when you have control over the compiler and can play with it. So if you want to try this on Vesta or on Mira or what have you, there are soft-env keys that you can load. If you use them, then your MPI-CC or MPI-CXX will give you this VG-Clang compiler setup that I've created. And as a special note, if you want a truly C++11 compliant programming environment, so you can use the new features that are found in C++11, including those from the standard library, there is a separate wrapper script that has 11 at the end of it, MPI C++11, that uses the libc++ subproject of LLVM to give you a C++ 2011 fully compliant programming environment that you can use on the BlueGenes. And at least currently, there is no other way of getting that. And openmp is currently under development, although not supported. That's the sort of main detractor for using this on the BlueGene, because obviously threading is somewhat important on that machine. So the question is, so he correctly points out that LLVM and Clang are used by many of those vendors for their OpenCL implementations. And is there a setup for using OpenCL on the BlueGene? That is actually something that we could do using that POCL project. It actually specifically has a setup which is quite good for that because it allows you to, POCL has a setup that allows you to statically compile the OpenCL kernels and then load them into the application ahead of time, which would be quite useful on the BlueGene because on the BlueGene, you really can't create at runtime executable pages. It's sort of a technical matter, but it would fit quite well. It's something that's sort of on my to-do list, but I haven't gotten to it yet. But if you have a use case, then I could move it higher on my to-do list. In any case, but it is something that I've thought about and something that we could certainly experiment with. And the same thing with the Ocelot project for running CUDA kernels. I sort of thought it'd be kind of neat to take codes that we're running on Titan or other machines, and just as a sort of portability experiment, say, OK, well, you can run them on the BlueGene also. Major set of features that are important for this on the BlueGene are features related to debugging. One thing which I worked on adding to Clang and to mpitch and to other things with some other people, which is now in upstream, in all these different projects, are MPI-specific warning messages. What this means in practice is that if you call MPI send and you set the data type to MPI double or something like that, and then the function itself just takes a void pointer, so it has no way of type checking that. But if you pass into the function a pointer which is actually, say, a float pointer, then you'll get a warning about it. And although it's a sort of simple feature, I caught several bugs in Hack just from those warning messages after they were enabled. So that was my first success story of getting some useful benefit out of this. And so have other people at this point, since these things have been on the machine. So that's quite useful. One thing that is additionally useful, which I've just gotten working recently, is the address sanitizer feature. That's a feature that lets you do bounds checking on arrays and dynamic allocations and other things. You can think of it sort of like Valgrind. The benefit of it is that it has much lower overhead than Valgrind. So Valgrind, you can take upwards of a 10 to 50 or what have you times performance hit, because Valgrind is actually emulating the processor as it runs the code. So it tends to be pretty slow. It's a very nice tool and quite powerful, but it's not fast. Since the address sanitizer feature works by instrumenting the code as it's being compiled, in other words, it embeds the checks into the assembly code as you compile the application, it has much lower overhead. And it works, which is the other nice thing about it. So part of the problem we have on the Blue Gene specifically is that we can't use Valgrind, because Valgrind doesn't understand the QPX vector instructions. And so if you have any kind of vectorized code in your application, then if you tried to run it with Valgrind, Valgrind would just die on you. This is additionally a problem because the MPI implementation has vector instructions in it. So even if you said, well, I'll just turn off all the optimization in my code and run it with Valgrind, it would probably work unless you called MPI all reduce or something, in which case your application would still die because Valgrind is emulating the processor, which means it emulates the MPI implementation, which means that it will die when it hits the vector instructions. And since I've had plenty of memory errors and other things that occur at scale and don't happen on my laptop, this ends up being quite useful, I hope. I've used it a couple of times since I got it working on some large codes. And another thing is the Clang static analyzer. As I mentioned before, symbolically executes pieces of code and produces more sophisticated warnings than you can get with a normal compile analysis. So if you want more information on this specifically, I put these things on the slides, mostly because obviously you can download the slides and thus you have the links. We have a mailing list, we have a track page, and I'm normally on this IRC chat room because I am the code owner for the PowerPC backend, among other things. You can also find me there. But for questions related to work on the Blue Gene, normally I think the mailing list is best, because that way other users who are also using it can have some idea what's going on. They can contribute answers to your questions, or at least find out from you what bugs they haven't hit yet. That was the end of the slide deck that I had. I did want to comment quickly in relationship to the discussion at the end of Anshu's talk about a concept that I've learned from the LLVM community is referred to sometimes as technical debt. I hadn't heard this term before last year or something. Apparently it is on Wikipedia, so it's some sort of legitimate. But so briefly, technical debt is the accumulated lack of documentation, lack of refactoring, and design work. Well, it's all of those things that you've put off and haven't done in your code project, and those accumulate over time, and this is the technical debt that's accumulated by the project. One of the nice things about projects that are relatively new is that they generally have a lack of technical debt. Since the project is new, there hasn't been a lot of time to put off things, and so a lot of, you have things that are still, cleanly designed and well documented and all this kind of stuff. As projects age, they obviously accumulate. In LLVM specifically, there really is an emphasis on avoiding this, but you can only accomplish that to a certain extent. Even though we try really hard to make sure the design stays clean and the documentation is up to date, it is still true that every contributor has deadlines and other forces that are impacting their priorities, and there is inevitably procrastination on these sort of deeper issues and documenting what you've done. So LLVM is a compiler, and often on the mailing list, every once in a while, you get some discussion that pops up comparing it to, say, GCC or to other projects, and why one is better than another or not, or what have you. And normally I sort of stay out of these things and don't really pay attention to them. But one point that is often brought up, which I think is reasonably useful to note, is just the fact that there is an important age factor in projects. There are, GCC, for instance, is old and has a lot of technical debt, right? But it's been around for a long time, probably longer than I've been programming. Right? So, whereas LLVM has not. It's a much newer project. It's still relatively clean. It also helps that it's in C++ and has better design principles and other things. But there's a certain amount of this is sort of independent of programming language and those sorts of concerns. And I think that that the same thing ends up being true for scientific codes. That you have, there's a threshold where that you reach for projects as they age, where it becomes not worthwhile to put a lot of time and effort into putting in new features because they've accumulated so much technical debt that that your sort of efficiency in working with them is very low. And I think that for a community project to be successful, you have to always keep this in mind. You have to always keep in mind exactly what your target longevity is, and really try and make sure that your accumulation of technical debt does not sink your project before it reaches its target longevity, whatever that happens to be. Maybe LLVM's target longevity is forever, but I don't think that's a practical viewpoint either. So, yeah. So I wanted to say that because I think it is a useful way of thinking about these things and something that you really should keep in mind for any project that you're developing, whether it's large or small.